All right, so we're going to start off with an example, okay? This is something that you guys may remember, maybe not sure. But we're going to start off with something like this. So 3 to the x equals 1 over 27. Now, I know that when you first learned this stuff, this is what you were supposed to do. You'd notice that, okay, I have a base 3 on the left side, and on the right side, 27 can be written as a base 3. So I could write it as 3 to the x equals to 1 over 3 to the third. And I need to make sure both bases match. So right now they're not matching. It's 1 over. So what I'm going to do is move that 3 to the third up. So that's 3 to the x equals 3 to the negative 3. And there's a definition in algebra that basically says that if b to the x is equal to b to the y, then x must be equal to y. In other words, if you have the same base and different powers, just set the powers equal to each other. So that means x must be equal to negative 3. And that's your answer. Okay, so this is the way you learned it before. There is another way to do this. Okay, so let me take a little bit of space right here on the side. I'll change the color just so you guys can see that it's different here. But another way to do this would be like this. If you have 3 to the x equal to 1 over 27, if you have a power that's a variable, you're going to want to bring it down. So what you do is you apply a natural log to both sides. Okay, so ln of 1 over 27. All right, so you apply a natural log to both sides. Now once you do that, that x comes out, and you have ln of 3. And then right here you have, let me write this down. Negative ln of 27. Now, if you're wondering how the heck did I do that, that's another property. Let me write this property down for you. It says if we have ln of a over b, then we can write it as negative ln of b over a. So it basically says you're allowed to switch the number inside to maybe get rid of the fraction if you want to. But if you do, if you flip the fraction on the inside, then make sure you make the natural log negative. Okay? So that's why I flipped 1 over 27. I made it just a 27. I didn't want to see it as a fraction. So I wrote it as 27, but in order to do that, I got to make it a negative natural log. Okay? That's a property we learned a while back too. I just don't know if you guys remember it. Anyway, continuing with what I was doing, I'm going to divide both sides by ln of 3. So x is equal to negative ln of 27 over ln of 3. Now just so you guys know, ln of 27, that's the same as 3 ln of 3. I'll show you. Usually you just punch this into your calculator, but just so you can see. Okay, but I'll show you guys what I'm talking about. So I'll put it right here. And then I'm going to bring the 3 to the front, that power of 3 to the front. Right? And since the natural logs of 3 can cancel out, you get your answer. So notice, same solution, two different ways to do it. Most people prefer the first method because it was easier, right? A lot less work. But every once in a while, you have to go about doing it this way, where you have to apply a natural log to both sides so that you could bring down a power. Because maybe you can't make the bases match. Right? If it was like 3 to the x equals 2, there's no way you can make the bases match in that case. So in order to make that power come down, you're going to have to apply natural logs. Okay? And again, this is review from trig algebra 2. I think we did that in algebra 2 at its earliest. But yeah, so here's the first method, the one in red, right? Which doesn't take a lot of time. You just kind of work with your powers and your bases and try to make them match up. So that's easy. That's the preferred way if you can match your bases. But if you cannot match your bases, then you have to go about it the way of the green work. Okay, where you apply natural logs to both sides and start whittling it down until you finally get some kind of solution. All right, now let me give you another example. Part B. I think I called that part A, right? Yeah, I did. So part B, log base 2. So this is a log, not a natural log, but a log base 2 of x equals to -4. Now, remember how with a natural log, the way you get rid of a natural log, we use the base e, right? Because e and natural log have the same base, even though we don't see it. Well, log has a base 2 here. So in order to get rid of that log, base 2, I'm going to use a base 2. So it's going to look like this. 2 log base 2 of x equals to 2 to the -4. Now the 2 log base 2 will cancel itself out. So all you're going to have is an x. And that's 2 to the -4. Okay, so you're done with this problem. You just got to kind of simplify it. So that'd be x is equal to 1 over 16. And that's it. And there's no like secondary way to do this. That's the way you do it. You apply a base to make the variable come out. Are we okay with that one? All right, so derivatives. Let's talk derivatives and integrals, and we'll be done here. So this is theorem 513. So derivatives for bases other than e. Derivatives for bases other than e. So the reason why they say it is because we already know the derivatives for e to the x, right? We know how to handle that. If it's e to the 3x, then you take the derivative of 3x first, and then just write e to the 3x, right? That's the process for a base e. But if it's not a base e, then how do you do it? So we start off with some prerequisite here, some information we need. So let a be a positive real number. So let a be a positive real number. That's the way we write it. Okay. A is an element of the real numbers that are positive, but they do say that a cannot equal to 1 though. Okay. And let u be a differentiable function of x. Differentiable function of x. Okay, so whenever you see the term a, that's just some positive real number. It could be a fraction or anything like that, decimals. Just can't be 1. And then let u be a differentiable function of x. So here we go. There are 4 definitions here, okay? d dx of a to the x. So some number other than e, okay? And not 1, of course. But like 2 to the x, 4 to the x, -3, actually it can't be a -3, I'm sorry. But like positive 3 to the x. That type of stuff. So if you have that, of a to the x, then your derivative is ln of a times a to the x. That's your derivative. Now I'll write this down and then I'm going to erase it, but I just want you guys to understand that this works for e to the x as well. Because according to the definition that they gave us, I'm supposed to write ln of e times e to the x. But what's ln of e? It's 1, so this is basically e to the x, right? Which is a definition I gave you in the last section. So this does work for the derivative of e, but they just didn't show it to us now. They showed it to us before. Okay? But this works for the definition of e as well. All right? So if you ever forget the derivative of e to the x, which I hope you don't, but if you ever do, you can do it this way, and you still will get it. Okay? So I'm going to erase it really quick because that's not something we need to worry about. You already have that in your notes from before. Second definition. So if you have d dx of a to the u, so now the general format. So you're going to do ln of a times a to the x times u prime. It's very much like the e to the x definition when it was e to the u, right? E to the u was u prime times e to the u. So it's the same thing. It's just missing the natural log part for it. But the reason why I was missing it for e is because ln of e is 1, so no reason to put it. So they do give us two other definitions, and these are for logs. Okay, so the derivative of a log base a of x. It's 1 over ln of a times x. And then, of course, they're going to have log base a of u, just in case you have to do something else other than an x inside of that log. So d dx of log base a of u, which will be 1 over ln of a times x times u prime. Notice for all these definitions, e to the u, a to the u, log base a to the u, you always just multiply it times u prime when you take a derivative. Right? That's the only difference. You're putting in a u prime at the end. So we'll try some examples. What is it? 3 examples, and then we're going to do the integration. We'll do an example, and then we're done. So a very quick lesson. So let's see, example number 2. So for example 2, we're just going to differentiate. Let's take a derivative. So we're going to take a derivative of y equals 4 to the x. So for y equals 4 to the x, then y prime will be, well, according to definition, if it's just an a to the x problem, you write ln of a times a to the x. So a is 4, so I'm going to write ln of 4 times 4 to the x. And I'm done. Now usually people prefer to write it like this, but it's okay if you don't. Okay, but there you go. So that's pretty easy. Let's try part B. We'll do f of x equal to 3 to the 2x. So that definition says that if you take a derivative of a to the u, then your answer would be ln of a times a to the u times u prime. That means I got to take a derivative of it, right? So f prime will be ln of 3 times a to the u, so it's 3 to the 2x, times the derivative of u. For me, u is 2x, right? That's the function up there. So derivative of 2x is 2. Okay? So the way I would probably write the answer for this, I would just write 2 times 3 to the 2x ln of 3. So kind of messy, but that's our solution. Now, some people would prefer it written like this. I'll show you. Whenever it looks this crazy, they kind of prefer writing it like this in some cases. And the reason why they do that is because then they say, oh, that 2 in the front can become a power. So ln of 3 squared. So this will actually be ln of 9 times 3 to the 2x, which actually we can rewrite it as 3 to the 2x ln of 9. So you can do that. Just kind of work with what's given to you. You'll notice sometimes the book will do that in its solutions. It's just trying to make it look as clean as possible. Okay? So whatever you feel like doing with that information, just as long as it's correct, right, should be okay. Let's do one more and then we'll move on to the integrals. Let's do one with logs. So y equal to log base 10 of cosine of x. Okay. So according to definition, for a log base a of u, right? It's not just x, not log of x, it's log of cosine of x. So this is log base a of u. It's supposed to be 1 over ln of a times u. Wait, did I write that properly? I didn't. Number 4. I apologize. Number 4. This should be a u. I wrote x by accident. It should be a u.
Number 2.
Uh-huh.
Yes.
Thank you. Let me fix those. In my head, it was right. My hand wrote it wrong. Thank you for that other correction. But yeah, those should be U's. I mean, the work we did is fine, so the examples are just fine. But yeah, definitions are going to be a little off. So there we go. We fixed them. So it's 1 over ln of a times u times a u prime, right? So for this, I'm going to write y prime equals to 1 over ln of 10 times cosine of x times the derivative of cosine of x, which would be negative sine of x. Now, if you're kind of looking at that, well, negative sine of x on top of a cosine of x becomes a what? It becomes a tangent, right? Negative tangent. So this will be negative tangent of x over ln of 10. Because remember, the negative sine of x over cosine of x, that's going to give you your negative tangent. So that's just going to be up on top. Are we okay with those three? Any questions? All right, so let's do integration. Then we have one problem to do on that, and then we're done. So, integration of bases other than e. So bases other than e. So here's your definition. The integral of a to the x dx is equal to 1 over ln of a times a to the x plus c. All right, so we'll just do a real quick example on this one. This would be example number 3. By the way, you can apply substitution to this, just so you're aware, okay? I mean, if it's a to the 3x plus 1, then you let u equal to 3x plus 1. Do your integration the way you normally would, and then, still follow the same rules. So here we go. The integral of, we'll just go 4 to the x since we did a 4 to the x last time. So integral of 4 to the x dx. So according to definition, you do 1 over ln of a is 4, so ln of 4 times a to the x, that'd be 4 to the x plus c. And that's your answer. If you want to write it together, 4 to the x over ln of 4 plus c, that's fine too. But it's based on definition. I don't actually have to use like a power rule or anything like that. It's just once it looks in that, like that form, then I just utilize the definition. Okay? So here's a little problem you might see. Just as an extra here, a bonus. Okay? So differentiate. Now this is not an integration problem, okay? Differentiate y equals x to the x. Now I told you guys that whenever your variable is up as a power, what do you introduce to basically bring it down? Natural logs, right? So we start off with y equal x to the x. And we're going to introduce a natural log to both sides. So ln of y equals ln of x to the x. Now, ln of y is going to stay the same for now, but this is x to the x times ln of x. Okay? So they want us to take a derivative of it. Alright, so they want us to take a derivative of this function. So the derivative of ln of y with respect to x is going to be 1 over y dy dx. Remember, I got to do this implicitly. Okay, I got to do this implicitly because I haven't solved for y by itself. So I have to do dy dx of everything. So there's dy dx times 1 over y. On the right side, it's going to be a product rule, right? So the derivative of x is 1 times ln of x plus x times the derivative of ln of x. That's 1 over x. So, whoops. Let's simplify the right side. Let me just write 1 over y dy dx equals to ln of x plus 1. Okay, that's what it looks like right now. Well, since they want me to do a derivative of this, right, that means they only want dy dx by itself. So I'm going to get that y and throw it over to the right side. So dy dx is equal to y times ln of x plus 1. Now, we're almost done. A lot of people would say, well, that's it. But no, we want our function to be in terms of x only. So I see a single y there. What is y equal to? X to the x. That was given to me in the very beginning, right? So I'm going to write dy dx is equal to x to the x ln of x plus 1. And that's your derivative for that function. All right, so here's your homework. Page 368, numbers 1 through 8. This is another one of those assignments where I kind of jump around, so I know it looks a lot worse than hopefully it really is, but I just don't want to make you do 80 problems. So that'll be it. Just giving you a little sprinkle of everything. That way you kind of try everything out. At least see it, so that if you ever see it again, you're going to say like, okay, I did stuff like that before. Let's see. So there you go.